we know that the span of different sets of vectors could actually produce the same subspace of the ambient vector space. With that in mind, let's have a look at this example. So let's compare these two spans. You see these sets of vectors that we're taking the span of are different, but the question is, right, each of these produces a subspace. Are these different subspaces? Well, thinking about whether the first one is in the second, this vector 1, 0, 0 and this vector 0, 1, 0, these vectors are both in this span, clearly, because they're in the spanning set. So the set containment this way is pretty clear, right? This span of 1, 0, 0 and 0, 1, 0 is the smallest vector space containing these two vectors. Well, here's another vector space containing these two vectors, 1, 0, 0 and 0, 1, 0. And so the span of just these two must be contained because it's the smallest such vector space, smallest such subspace. All right, so what about the other containment? So containment this way. Well, 1, 0, 0 is definitely in this span. 0, 1, 0 is also definitely in this span. Well, what about 2, 3, 0? Well, 2, 3, 0, I mean, pretty clearly it's 2 times 1, 0, 0 plus 3 times 0, 1, 0. And so the vector 2, 3, 0 is also in this span, right? So all of these three spanning vectors are in this subspace. But that means the span of these three vectors is also contained in this subspace because this span is the smallest subspace containing these three spanning vectors. So that gives us the containment the other way. So actually, these two subspaces are exactly the same subspace, which, on the one hand, we knew that could happen. We've seen examples before where spans of different sets produce the same subspace. But I think the surprising thing in this example is that this second way of generating this subspace as the span of these three vectors, it has this extra vector in here, right? Since these two subspaces are the same, what this is really telling us is that this third vector, 2, 3, 0, it's not really necessary to generate this subspace, right? It's sort of extra. It's kind of redundant. So what is it about this vector that makes this redundant to generating this subspace? Well, really, it's this over here. It's because this extra vector that we had is a linear combination of the vectors we already had in our spanning set. So to try to describe the redundancy that's happening, we'll use this language of linear combinations. Okay, so the exact vocabulary that we'll use is linear dependence. So if we have a vector that can be written as a linear combination of some others, then we will say that that vector v is linearly dependent on those vectors, v1 through vk. So in other words, they're scalars a1 through ak, so that v is a1 times v1 plus all the way up to ak times vk. If v cannot be written as a linear combination of v1 through vk, so if v is not linearly dependent, we will say that v is linearly independent. All right, so just for an example, let's show that this vector is linearly dependent on these two vectors. Okay, so remember, linearly dependent, that's just yet another way of saying is a linear combination of. Right? For now, that's what that phrase really means. And we know how to check if one vector is a linear combination of two others. Right? What we need to know is there a solution to this equation, right, this vector equation? And we know that, so a2 times minus 1, 2, 2. We know that we can answer this question just by solving this linear system. So write down the augmented matrix corresponding to this system, which for some reason I seem to be unable to do. So that should be a 5 and 3, and then minus 1, 2, 2, and then our augmented column is minus 7, 16, 0. So yet another row reduction to do here. So let's see, why don't we divide the first row by 2, I guess. So 1 minus a half minus 7 halves minus 5, 2, 16, and then 3, 2, 0. And now we can zero out some entries. So we need R2 plus 5 times R1, and R3 minus 3 times R1. Okay, so that gives us 1 minus a half minus 7 halves. And then, let's see, 0, and then minus a half, and then, oh boy, 5 times 7, so 35 halves, negative 35 halves plus 32 halves, so minus 3 halves. Oof. Okay, and then last row, 0, so this minus 3 times that, so 4 halves plus 3 halves is 7 halves, and then 0 plus 21 halves, 21 halves. Okay, now I guess we can multiply the second row by minus 2, and while we're at it, let's multiply the third row by 2/7. Right, that's going to make the fractions nice. So 1 minus a half minus 7 halves, 0, 1, and 3, and then 0, 1, and 3. Okay, so at this point, right, if you're sort of used to thinking about how augmented matrices correspond to solutions, you might be able to identify already that this will have a solution. But just to be explicit about it, let's do row 1 plus 1/2 row 2 and row 3 minus row 2, just to get all the way to reduced row echelon form. So 1, 0, and then let's see, plus 1/2 this, so minus 4 halves, so minus 2, and then 0, 1, 3, and then this one's going to be all zeros. Okay, so right, this is telling us the coefficient for the first column, and this is telling us the coefficient for that column. So minus 7, 16, 0 is linearly dependent on the other two because it's minus 2 times minus, 2 minus 5, 3, plus 3 times minus 1, 2, 2. Okay. All right, so this is linearly dependent on these two. All right, so that's how we can show that one vector is linearly dependent on a couple others. What about showing that it's linearly independent? So remember, linear independence, that would mean that V cannot be written as a linear combination of these other two. So in other words, right, if we write this linear system that I hope by now you're kind of tired of watching me write. So if we're going to have linear independence, then this should have no solutions, right? That would mean that 1, 4, 2 is not a linear combination of the other two vectors. So we can play the same game. And augment with 1, 4, 2. Right. All right. You know what I'm going to do to make it easier on myself? I should have done this on the first one. I'm actually going to write these in the other order, just because it's going to make the arithmetic easier. Right. Okay. So -1, 2, 2. 2 minus 5, 3. I should have done this on the other one. Would have made the row reduction a lot easier. So now we can do row 1, take the negative of row 1. We'll also take row 2 and add 2 times row 1. And we'll take row 3 and add 2 times row 1. Yes, this is much easier. I really should have done this the first time. Okay, so 1 minus 2 minus 1. 0 minus 1, 6. And 0, 7, 4. Okay. And now we can do row 3 plus 7 times row 2. We get 1 minus 2 minus 1, 0 minus 1, 6, 0, 0. And then, let's see, 7 times 6 is 42, plus 4 is 46. Okay. And if you look at this system, because this is an augmented matrix representing a non-homogeneous linear system, this has no solutions because of this row, right? No solutions. All right. So that means that V is linearly independent of the others, V1 and V2. All right, so linear dependence and independence of a collection of vectors, at this point it is basically almost the same as being a linear combination of, and it seems to be capturing this property of being redundant, right? It seems like we're capturing, if we look at our example that inspired this situation, right? This vector, 2, 3, 0, is clearly a linear combination of these two, and so it's redundant somehow. It's not adding anything new to our span. So it seems like this definition of linear dependence and independence is capturing the redundancy idea that we were getting at.